So I've now made a function. I know what it means. I made a table that allows me to predict how many students are enrolled. So after 0 years, 2,000 students. This is the one that's going down, that's decreasing, so it belongs to Kennedy High School. Just really quickly go back to compare these two again. King High School, the input was the year, starting with 0 for 2005, and you output the population. King is growing by 2% every year, and it's starting at 2,000 students, and so the function was 2,000 times 1.02 raised to the x. And that's the function that I have put into, the function that I put in here incorrectly. It was only 2% that it was growing by. So that is the function for King High School that I put into y2, and then for y1, same thing. The input was the number of years, the output is the population. It's decreasing by 3%, so the base or the growth factor is 0.97. That's 3% lower than 100%. Coefficient is again 2,000 to start with, and that means my function is 2,000 to start with times 97% to the x power. And I'm going to graph both of those things now that I have a data table. So I put together the function, and then I use the function to make this data table. And now that I have a data table, I can graph both King and Kennedy High School so that I have an idea of what their population is doing. On the left-hand side, I've started here at year 0, that's 2005, going up to year 6, that's 2011. And then the population starting at 2000 is decreasing here for Kennedy High School, that's the one that's losing population, and increasing for the other school. And this comes from my old data. Alright, don't panic. I just changed y2 to reflect the fact that King High School had a growth rate of 2%, not a growth rate of 3%. So let's graph both of these functions, the two high schools, Kennedy and King, on the same graph. The domain here, first of all, the variables. I'm growing in the x sense by years, and that's since 2005, and it's a lot easier to do since 2005, which is the reason why. Let me just prove that to you. If you were modeling a function and you didn't replace the x with 0, if you didn't start it at 0 instead of starting it at 2005, then your function would look something like 2,000 times 97%. And then to the x, well, if this x was the year 2005, then that means that you're multiplying 0.97 2,005 times. In other words, I would have to write this number 2,005 times out. And that would be if it was growing for that duration of time. So it's way easier to start at 0 and then count 1 time, 2 times, 3 times, and so on. So a lot easier to write the function so long as it starts at 0. And you can see that I've done that. It's reflected in the data set here, that it starts at 0. That's the year 2005. And I'm also going to have it be reflected in the graph here starting at 0. Now, 0 means 2005. And then 1, 2, 3, 4, 5, 6. That's 1 year, 2 years, 3 years, 4 years, 5, 6 years. So, for example, 2006, 2007, 2008, 2009, this is 2010. Okay, so 5 in the model is the same as the year 2010. And now the domain, or rather the range, the biggest number is here and the smallest number is here. So I'm going to go down all the way to 1,500 would work in the range, and up to 2,500, and that's for the population of students. And then I can break that up. Actually, I'm going to want to go halfway, and halfway be 2,000, and then halfway here be 1,750. Halfway here be 2,250. Now, not enough time, there's so little time that's gone by in these two graphs. Let's just look at what they're going to look like. So first I'm going to set my window to something that makes sense. We're starting at 0 and going up to 6. by counting by ones. I'm setting up my calculator to start at 0 and go up to 6, start at 0 and go up to 6, counting by ones. And then the minimum is 1,500. So 1,500 is the smallest number that I want to bother with, and 2,500 is what it goes up to. And I'm counting here by 250. So if I were to graph this, the first line, the Kennedy line, is going to be decreasing at a rate of 3%. And then the other line, the King line, is going to be increasing at a rate of 2%. Now you can see that the King line is a little bit more, changing a little bit more slowly than the Kennedy line, because it's 2% versus 3%. The other thing that you'll notice is that this is not a curved line like you would expect it to. So again, I'm expecting this graph to be here. And the reason why you can't see the curve is because we didn't let the years go out as long as they needed to. It's going to take a very long time. If you change by 2% a year, it takes a very long time to make a measurable difference. So what if we went out 100 years? That's enough time, too much time. You can very immediately see the difference. So that's so much time that it looks straight again. So it looks like maybe 10 years would be enough here. Let's try 20. You can just start to see the curve. No, these still look like straight lines to me. So let's zoom out just a little bit more to maybe 50 years. 40 years. Oh, I see. They terminate before you can see the curve. Well, this one at least you can kind of see. Okay, so I had to mess around until I went all the way out to 100 years, and then I also had to change the domain and range to be big enough to be able to see the curve. What this was all about was when I graph it over here, it's going to look like it's a straight line, but that's only because I'm zoomed into just this little part of it. And if I were to be able to zoom out more, I would be able to see the curviness of it. And that's very true for most of the time when you're taking data. If I was taking these data, like I was measuring these things, I wouldn't be able to tell that it was exponential until I took a big enough domain and until I changed the independent variable enough. So a lot of the times people think that situations are linear, that they're really not. So let me do, in red, I'm going to do the one that was shrinking, and that's Kennedy. And then in blue, I'll do the one that was growing, and that's King. And these are going to come out looking like straight lines because I'm so zoomed in. So I'm starting King at 2000, and then 2040 is just a little bit of a change. Let me go all the way out to 6, which is 2,250, which is all the way out there. So I'm going to do my two that are furthest out so that I can get fairly close to what this is going to be. And don't connect this dot with a straight line. It's going to be a line that's very slightly curving upwards by 3%. So this is the line for King High School, and it's growing by 3% a year. And then if I do the same thing for Kennedy, it's starting at 2000s, and it's decreasing here until 1665 out to the end. So year 6, that would be 1660, maybe 1665, about right there. And then 1, 1940, 2, 3, 4, 5, something like this. And this one has an inflection that's going a little bit up. In other words, this is curving a little bit up, whereas this was getting steeper. This one's getting less steep, whereas this one's getting steeper. So Kennedy is declining by 3%, and here I am, I think I'm getting this wrong again. This should have been a 2% rate of growth. Okay, so there's a couple of other questions that I'm going to ask from there. One is if the model holds true, how many students will there be at King in 2013? Now, King is the one that's growing, so I expect more than 2,000. And let's figure out what year I want here. So I want year 2013. but I started at 2005. So my graph doesn't quite have it, and neither does my table. So I want to go all the way down. So this is year 0, so this would be year 2005, 2006, 2007, 2008, 2009, 10, 11, that's 2011 down here. It wanted 2013, so 2012, 2013. So I want to go 2 more down. In other words, I'm trying to figure out, let's see what the difference here would be. This would be year what? So let's subtract. 13 minus 5 is 8. So that's year 8 that I want. Okay, so I'm going to replace in the function y equals 2,000 to start with times 97%. Oop, this is the one that's growing. Times 102%. To the x power, I'm going to replace that with 8 and see what I get here. So let's go to the table and go to year 8. Year 8 is 2,343. I'm looking at this line here. This is the one that's growing. That's the one that we want in King High School, and it's at year 8 or the year 2013. In our, if I add 2005 to 8, 2,343 people, which is right there. Might be easier for you to see just doing it this way. 2,000 people to start with times 102% raised to 8 years. This is 2,343 people. And now we want the next question. What year will there be 1,400 students? So I'm working backwards here. So let's see, this was Kennedy High School, and I want to go down here until I reach 1,400 students. So at what time does that happen? So how many years do I get down to 1,400? And easiest way to do that again is with the table. So I'm going to keep going down, and it occurs between here and here. If I wanted to get it exact, I could find the intersection, but the important thing is that it occurs during year 11. So between year 11 and year 12. And the way that I interpret that in the problem, it happens in year 11. Again, in year 11, I'm reaching 1,400 students at Kennedy High School, year 11 right here. And then if I started in year 2005, and added 11 years to that, then that would be 2016. So Kennedy High School is going to be almost empty. It's lost 600 students by the time it gets to 2016.